Yeah, so good morning. So, in today's lecture, we will discuss again few cosets, whatever we discussed last day, and then we will define a few new ideas, and we will create some new groups from existing group. So, let us start with recalling. So, recall that we define something called cosets, or rather left cosets. So what was that? So you have a group G and a subgroup H. Okay, and then you define a binary operator tilde on G by what? So we define that G is related to some G dash if G equal to G dash H for some H belongs to H. Okay, and then we check that this becomes the tilde is an equivalence relation. Okay, and the equivalent classes with respect to that operation, we define this by these symbols. Okay, left cosets, so they are the left coset of H, right? Similarly, you can define something called left coset by G. Okay, similarly, you can define something called right coset. Okay, and so right coset of G you can define by Hg. Okay, right coset of H by G, and in this case you need to define tilde on G by this. So you will say that G related to G dash if G equal to H G dash for some H belongs to H, right? And similarly, you can check again this tilde or whatever tilde dash tilde dash tilde dash is also equivalent relation, and the equivalent classes are actually this right cosets. Okay, so anyway, and also we showed that it has few properties. For example, the basic important property is that if AH equal to H, this implies and implied by A belongs to H for any A belongs to, yeah, this is for any A belongs to G. Okay, similarly, another property is that AH equal to BH, and this is if and only if B inverse A belongs to H, right? This property you already know, right? Now, if I collect this one type of coset, for example, if I collect the left cosets, so let me collect it. So let me collect, um, say collection of all distinct. You know that this is equivalent class, right? They are either disjoint or they are same, right? So when I'm saying distinct, I mean that I'm collecting disjoint things. Okay, so distinct left cosets of H. Okay, and this collection I will write down by this symbol G mod H. So I have a collection which is collection of all the left coset, distinct left coset of H. Okay, and I will define operation on H. So let us define this operation on H by this symbol, say G1H with G2H, and this operation is by this is definition. and defining this thing G1 G2 H. Okay, G1 G2 H. Now you check that this operation is a nice operation. It satisfies few properties, nice properties. For example, it's associative, right? So you check that uh, check that this is associative. What does that mean? So if you have this um, uh, this dot, okay, so this into this dot, sorry, dot, okay, and this is nothing but first you do G1H into G2 G3 of H, and then it is again this G1 G2 of G3 of H, which you can write down as G1 H dot G2 H of G3 H, right? So this associative property is there, and also you check that with respect to this operation you have, so this is associative, right? Now with respect to that you have a nice element, say you write down 1 H is by H, 1 is the identity of the group G, okay, and also H. So so this is a nice element, so this actually has this property. So for any G belongs to G, you have GH dot 1H is equal to GH equal to 1H dot GH, right? So what does that mean? That means this operation, if I do operation on with these elements 1H or H, then that will keep the element same. So this is kind of working as an identity, right? So this H is the identity with respect to this operation dot on this G mod H, right, on the set. So right now I have no idea, I just know that H is a subgroup of G, and I'm trying to check whether this operation makes G mod H is a group or not. Okay, now you check the inverse also. So for third property, this is second property, this is first property. Okay, now to check it for third property, for any G belongs to G, we have the inverse, right? G inverse also belongs to G, sorry, G inverse belongs to G, so you can write down G H into G inverse H, and this is same as H is same as G inverse H of GH. So what does that mean? That means so this means that you can define the inverse of these cosets by this, the inverse of H, right? So apparently it looks that this operation actually kind of nice operation on G mod H, the collection of distinct left cosets. You can play the game with the right cosets also, no problem. Let me do it for left cosets, and apparently look like that it forms a group, right, with respect to this operation. Yeah, but there is a point. So see here, um, we did not we did not check. So yeah, let me write down this S, G mod H as by S. So this is kind of dot is a map from S cross S to S, right? What you need for a group. But you say that this this I did not check whether this map is only fan or not. What does that mean? That means if you collect two elements from here, this set, which are same, the image will be same. Yeah, so now if we, yeah, so if we collect yeah, two element which is same here, the image will be same here. Okay, so what does that mean? That means inside is if we collect um, two elements which are not same, then image cannot be same here. Okay, pre-image cannot be same here. So that part we need to check it. So how do you check this part? So let me check whether it satisfy or not, or under what condition it satisfy. Um, so what we need to check? We need to check that this operation is well defined or not. So um, so let you have to say you choose two elements from G mod H. Okay, so G, yeah, so from this S. So write down G. Okay, so let me write down some different symbol. It will be easy for us. Okay, so you choose say U H and VH. This is one element in S, and also you choose some U1H and V1H also in S, such that they are equal, such that they are equal. So what does that mean? That means so equal as a tuple. So equal as a tuple means that they are each component is equal, right? Okay, so that is UH equal to U1H and VH equal to V1H, right? That is again equivalent to saying that U and U1 both are element of UH. Similarly, V and V1 element of VH. Okay, the left cosets. Now, if this is given, what we need to prove? So we need to prove that the operation is well defined means what? That image of these tuples are same. What is the image of this tuple? The image of this tuple is UVH. Okay, and image of this tuple is U1 V1H. Okay, clear. So now can we check that image of these two tuples are same? How do we check? What condition is required to check these two things are same? Okay, this is an important question. Okay, so to prove these things, so let me just define this proposition. Now this proposition tells us that this whatever we discussed, this star from S cross S to S is well defined if and only if for if and only if for all G belongs to G and H belongs to H, we have G, H, G inverse is the element of H. So this is the necessary and sufficient condition for the operation to be well defined. Now how to prove this thing? Uh, so this proof is, let me continue from here. Okay. So I need to prove that UVH equal to U1 V1H if I assume this condition. Okay. So let us assume. So let us assume that GH G inverse is element of H for all G belongs to G and H belongs to H. Now can I prove this? Can I prove UVH equal to U1 V1H? Of course we can prove now, because now you see that uh, now okay, how to prove this thing? See here, you remember that you know that U and U1 are element of UH, right? So what does that mean? That means you can write down U1 equal to U times some H1. Similarly, you can write down V1 equal to V times some H2, right? This is So from here you can easily find out that uh, U1, U2, U1, V1 of H, U1, V1 of H is nothing but uh, UH1 into V1, sorry, VH2, right? So I just choose the values of U1 and V1 by UH1, VH2, because you know that U1 belongs to UH, so it will be of this forms. Now this is, I can write down as UV and then V inverse. Okay, so let me insert this part here, and then H1 V H2 of H, capital H. Okay. Now, just use associativity. Associative property tells us that U1 V1 of H is nothing but UV, and then what we have, V1 inverse V inverse H1 V, right? So V inverse H1 V and then H2 of H. Now you just recall that what I assume? I assume that GH inverse element of H for all G, right? Now here you choose G equal to V inverse. Then what happened? Then this is kind of GH1 G inverse, which is element of H. So this element is nothing but some H3. So you can write down as UV H3 H2. Again H2 H3 will become some H4, right? So this is again element of H. So this is nothing but UV of H, right? So what I just proved, that U1 V1 of H is nothing but UV of H. So what does that mean? That means that my question, original question, that um, whether these two are same. So these two are same under what condition? Under this condition, GH inverse belongs to H for everything, right? Yeah. So one part is we just proved the one part, but this is if and only, right? So we need to prove the converse part also. Now converse for how to prove? So let us prove this conversely. Um, Conversely, what is given? Given that if uh, UH equal to U1H and VH equal to V2H, so V1H, then this implies that U V of H equal to U1 V1 of U1 V1 of H. Okay, this is given. Okay, this is given. This part is given, and now I need to prove that for any G and H, right? So now let G belongs to G and H belongs to H arbitrary elements. So you have two arbitrary elements, you choose one from G, one from H. Now I need to prove that GH G inverse belongs to this set. Now how do you choose U and V so that it becomes it falls inside the property? So now you choose that you right now to use this above property, you choose say U equal to say 1 and U1 equal to something say H, right? Because UH equal to U1H, so if you choose equal to 1, it's identical, right? So you can write down U1 equal to H, so that H is nothing but element of U, right? Element of H. Clear? So, or rather, you can write down U inverse also, no problem. So let me write down by this. So, or rather, let me write down H1. Otherwise, there will be mix. Okay, C1 equal to H1, and for V, so we can write down that both V and V inverse. I'm using this symbol, say G inverse. Okay. Now, if you substitute inside this identity, so what happens? So it will have 1 times G inverse of H will be equal to H1 times G inverse. Okay. Oh, yeah. So no, I think okay for any H. So so what you can do? I just choose the same H. Okay, not H1. Okay, so this is same H. Yes. So then what happens? So 1 times G inverse of H equal to H G inverse of H, right? Clear? So this is I am using this identity, and then this will give. So now we multiply both sides by G, and then you will have G H G inverse of H equal to H, right? And which is nothing but that means that GH G inverse is element of H. This is a property of cosets. Okay. What do we prove? That if you assume the well-defined property, then for every G belongs to G and every H belongs to H, GH G inverse belongs to H, right? So this is kind of a nice property which is required so that you can make this. So thus uh, mm, uh, if we assume this property, assume GH G inverse belongs to H for all G belongs to G and H belongs to H, then what happen? Then G mod H uh, forms a group. Okay, this forms a group uh, under that operation under dot. Okay, so whatever dot we define under the okay, let me write down this multiplication of cosets operation. Okay, so under that same operation it becomes a group. Okay, clear? So what does mean? That means that given any group G and any subgroup of H, you can define the binary relation on G using H, and you can make those are equivalent relation such that equivalent classes become um, something called cosets. Okay, either you can do by left cosets or right cosets, doesn't matter. Okay, now what you can do, you want to make that collection of cosets as a group. Okay, and to make collection of cosets as a group, you need some property which is not always obvious from given any age, right? And then what does that mean? You need something more. You need something more, and this more will gives you some nice properties. So let us define by this proposition. So let G be a group and H be a subgroup of G. Okay, then the following the okay then the following are equivalent. What are the equivalent things? That number one, what we just proved, that for all G belongs to G, H belongs to H, G, H, ah, G, H, G inverse element of H. Number two, again for all G belongs to G, G capital H, G inverse subset of H. Number three, for all G belongs to G, uh, G capital H, G inverse is actually equal to H. Okay, and number four, now if we define a set by this collection of all G belongs to G, such that GH, G inverse equal to H, this set. Okay, if you collect this set is equal to G. Okay, so what does that mean? That means well, let me write down this name. So this is called actually normalizer of H in. Okay, so this is called normalizer of H in G. Okay, so this normalizer of H in G is actually G. Okay, these are all equivalent. Okay, also you can write down that this operations for all G belongs to G, the left cosets of G, H with respect to G is same as the right cosets. Okay, these all are equivalent. Okay, you can do one equal to another equal to one. These are homework, simple problem. Okay, now if H satisfies any of the above condition, whatever condition I just wrote, 5, 6, there are many more, but let us just stick with this. Any of the above conditions, then we say H is a normal subgroup. Normal subgroup, very important proper definition of G. Okay, then we say H is a normal subgroup of G. Okay, in this case we will write down H, not this was only subgroup. Now we will add this thing, and then this become normal subgroup. H normal subgroup of G, right? So clear. So um, mm, if your subgroup satisfy any of these condition, any 4 5 conditions, uh, any means anyone, all are equivalent. So if you satisfy find that one, then everything is same, right? Then we say that H is an all subgroup, and in this case you can define uh, G mod H makes a group, makes, like this. The operation makes a group, right? Group, if and only if H is a normal subgroup G. Okay. Otherwise, what you can say, you can always say that um, your G mod H is a collection of left cosets, or you can say right cosets, whatever. I am doing with the left cosets. Okay, you can do the game with the right cosets also. So these elements are all the cosets of H in G, but they need not be forms a group with respect to the multiplication by cosets. Uh, that quotient multiplication, okay, one to multiplication. But if you have this condition, H is an odd subgroup of G, then it makes a group. Okay, so okay, and also you can define something here. So you can what I just so this remember these elements, so G, H, G inverse are okay. So so it's R here. So is called the um, conjugation conjugate of H by G. Okay, and you can also write down G capital H. So this is as a set. So what is this? This means this is the set of the element of these forms such that H belongs to H. Okay, so you would collect any H and then multiply G H inverse and collect all the elements. They will be of these forms. Okay, so and these are called conjugates of H. Conjugate of H, the subgroup H. Okay, clearly. So and also I need to define one more definition here. Another definition, let me define something called center. So given a group G, I define ZG, and this is my definition. All G belongs to collection of G belongs to G, such that G dash equal to G dash G for all G dash belongs to G. So this is collection of every elements, collection of all the elements which commutes every element of G, and this is called the center of the group G. Clear? So this is called center of G, and this definition will play a role in near future. You will show that. Okay. So so we learn the normalizer. So what is the meaning of normalizer actually? So yeah, so I define normalizer right here. See, so you can ask one property. Okay, you check that this NGH is the largest subgroup of G, obviously containing H such that H is a normal subgroup of NGH. Okay, so given any group G and any subgroup H may not be normal inside G, but H is always normal inside the normalizer. Okay, So the proofs are very simple. So first you need to check that NGH is a subgroup of G, and that is obvious. So check that NGH is a subgroup of G. Okay, and number two, you check that H is a subgroup of NGH first of all. Okay, so yeah, so H contain this is obvious because I mean this is obvious, right? H is a first of all subset of this, because for any H belongs to as for all H belongs to H, you have H, you choose any elements, H1, H inverse, these are always element of H, right? This is just a, group operation on H, right? So what does that mean? That means every H is coming, every H is actually normalized. This is then we call that H normalized this element, right? For inside, in fact, in this case, we write down that the element G normalize H. Okay. So H is a subgroup of subset of NGH is obvious. Now we need to check that H is a subgroup of this, and that is also obvious. Both are group, so one subset of another, so subgroup. Now how to check that last part, that to check H is a normal subgroup of NGH. What you need to check? You need to check that given any element from, okay, so what I need to do, um, let G belongs to this and H belongs to H arbitrarily, right? B to arbitrary element. Now what I need to check? I need to check that G inverse element of H, right? But by definition, G inverse belongs to H, because this is a definition of normalizer, right? So it's obvious, right? Proofs are obvious by definition. Okay. So G inverse belongs to H, and hence H is a normal subgroup of normalizer of H in G. Clear? So these are small observations you should learn. And one more nice property, or you can write down proposition or whatever theorem. You should prove that is a subgroup H of G is normal. How to check that something is normal or not in by other way? And obviously this is definition, but can you prove by the way? Yes, the answer is that if and only uh, H is the kernel of some homomorphism, some homomorphism, from G to some group. Okay. How to prove this kind of statement? So again, there are if and only conditions, means there are two conditions. One, if you know the H is a normal subgroup, then it is homomorphism. And another thing is that other. So first part, let us prove that let H is a normal subgroup of G. Then I need to prove that H is kernel of some homomorphism, right? Now if H is a normal subgroup of G, then we know that we have the group G mod H, and this group is also, okay, so let me write down here. So this group is called quotient group or factored group. Okay, so where did I write? Okay, Yes, so this group is called the G mod H makes a group, and this is called the factor groups, factor group or quotient group, quotient group. Okay, so anyway, so whatever you feel you can write down, quotient group, factor group, doesn't matter. Okay, so what I was discussing is, so G mod H is a quotient group or factor group, and then you can define from G to G mod H a map phi such that phi of G then a shell map going to the cosets. Okay, now you check that. Now this is obvious, you check that homework. Okay, that this kernel of phi is nothing but H. Okay, so one plus we just proved that H is a kernel of some homomorphism, right? Now conversely, if if uh, H is a kernel of uh, some homomorphism, or rather I should write down let H is a subgroup of some homomorphism. Then what happened? So um, okay, so homomorphism. Then I need to prove that a kernel of homomorphism is a normal subgroup. Now kernel is a subgroup we know already, right? Now how to prove kernel is normal subgroup? So let you choose um, uh, G belongs to that group G and H belongs to that H, which is the kernel of some phi. Okay, homomorphism phi. So, and then what you need to prove that? You need to prove that GH inverse belongs to this thing, right? GH belongs to kernel means what? You need to prove that phi of GH inverse is identity, right? But phi of GH inverse is nothing but phi G, phi H, and phi of G inverse, right? But phi of G inverse is nothing but phi G whole inverse, so you can write down that. Uh, yeah, so but see H belongs to kernel, so what does that mean? That means phi of H equal to 1, right? And this part get cancelled, so you have phi G and phi G inverse, right? And this is again equal to 1, identity. So GH inverse again inside the kernel, so this GH inverse is again inside the kernel, which is the subgroup H. Okay, so these are obvious proofs, so we can easily find out that um, GH inverse is a uh, yeah, so we can find out that a group H is an also if only it is a kernel of some homomorphism, right? Now you can have some examples. So let me give some example of this. Now, so you have a group G, and then there are trivial examples. So what are the trivial examples? So this identity and G are always um, normal subgroup, right? Normal subgroups of G, they're always right. And what happen if G is abelian? So if G is abelian, then check that, then every subgroups of G, every subgroup is normal. This is a simple fact. You can easily find out that abelianness will gives you this. So for any subgroup G, you write down G inverse, and this is abelian. So what does that mean? That means the commutes, right? So this is nothing but G inverse, which is nothing but H. Okay, so it is actually more G inverse equal to H pointwise. So note that here when I am writing the G inverse belongs to H. Okay, rather yeah, where did I write? Yeah, so these are as a set wise they are equal, not point wise. So what does that mean? That means so G inverse belongs to H, and that means that G inverse equal to so this means that G inverse equal to some H dash, okay, some other element, and in H dash some element, it may be equal, may not be equal, right? This is the meaning of this. But you check that here, when G is abelian, then they are equal actually. G inverse is actually equal to H, right? So for abelian groups, every subgroup is non-subgroup, right? Now what happened? Maybe I can give another example. So number 3. Now you have a group G, and you have the center. Okay. If you choose any subgroup which is a subset of center, okay, that means which is element sitting inside center. So is normal. So what does that mean? So it says that any central subgroups is normal. Any subgroup which is sitting inside center is normal, and that is obvious again, because if it is sitting inside center, and then you write down G inverse, because H is an element of center, so it commutes, so it is H G inverse H, right? Element of H. So central subgroups are always normal subgroups. Okay, so yeah, so maybe I should stop today's lecture, and that ends today's lecture. And I am going to send you that tutorial also, and submit this tutorial by 20th September, Sunday, okay, midnight Sunday, to the by email to the TS, and you can say you have to send me a copy also, so you can CC to me, send it to Sonam and IIT and CC to me. Okay, so this ends today's talk. Please write down your comments and questions below this session. Okay, bye.